In this slide, we'll be talking about relative humidity and some associated terms, some situation that would be very important here. So far we have discussed the amount of moisture actually in the air and how much more would be needed to saturate the air. We have several options for describing the amount of moisture in the air. So we talked about absolute humidity, that tells us the mass of water vapor in a fixed volume of air, or the water vapor density. We also talked about specific humidity, that measures the mass of the water vapor in a fixed total mass of air. And the mixing ratio we also talked about, which describes the mass of the water vapor in a fixed mass of the remaining dry air. We also talked about the actual vapor pressure of air, which expresses the amount of water vapor in terms of the amount of pressure that the water vapor molecule exerted. We also have an option for describing how much moisture could be added to the atmosphere. So we talked about the saturation vapor pressure. This describes the pressure that the water vapor molecule would exert if the air was saturated with vapor at a given temperature. So each of these that we talked before measures has its uses, but as well as we see the concept of vapor pressure and saturation vapor pressure are critical for an understanding of the relative humidity. So what is in the relative humidity, we'll see it is the most commonly used the describing the atmospheric moisture. In our weather app, when we see the humidity, actually it is telling you the relative humidity. It is also unfortunate, the most misunderstood, that when we see the humidity, we are actually watching relative humidity. The concept of the relative humidity may at first seem confusing because it does not indicate the actual amount of water vapor in the air. Well, instead of that, it tells us how close the air is to be saturated. This is the main things here. So the relative humidity we can call is the ratio of the amount of water vapor actually in the air to the maximum amount of the water vapor required for a saturation condition at that particular temperature and pressure. It is a little complex. Let's look at the equation here. If it is the ratio of the air water vapor content to its capacity, so relative humidity would be water vapor content over here, water vapor content divided by water vapor capacity. We can think the actual vapor pressure as a measure of air actual water vapor content, and the saturation vapor pressure as a measure of air total capacity for water vapor. So, if we would like to say the equation in other way, we will say relative humidity is equal to actual vapor pressure divided by saturation vapor pressure, and we know that the relative humidity always be in a ratio. Then we are multiplying that 100 and we're adding percent. So percent mean always 1 by 100. Okay, so relative humidity is given as a percent. The air with 50% relative humidity actually contain one half of the amount of water vapor required for saturation. Air with a 100% relative humidity is said to be saturated because it is filled to capacity with water vapor. The air, what would happen is a more than 100%. So air with a relative humidity greater than 100% is said to be supersaturated, a condition that does not normally occur and normally actually last long. Since relative humidity is used so much in the everyday world, let's see more closely some things. So relative humidity, a change in a relative humidity can be brought about two primary ways. So when we would like to change the relative humidity, we have to do either of them. So we can change our relative humidity by changing the air water vapor content. Also, to change the relative humidity, we can change the air temperature. So this is the way we can change the relative humidity. So if you are looking at over here, over this picture, if you look this one very closely, you will have an understanding of the relative humidity. Okay. Now, water vapor content of the air with no change of air temperature increase the air relative humidity. The reason for this increase is that the fact that the more water vapor molecule are added to the air, and there is a greater likelihood that some of the vapor molecule will stick together and condense. If more and more water added, condensation will occur. So condensation takes place in saturated air. So as more and more water vapor molecule are added to the air gradually approaches towards the saturation condition and the relative humidity of the air increases. So in other way, conversely, we can see the removing water vapor from the air decreases the likelihood of saturation, which lowered the air relative humidity. So in brief, we can say with no change in air temperature, if the situation is something like that, with no change in air temperature, adding water vapor to the air increase the relative humidity, and removing the water vapor from the air lower the relative humidity. But given the situation, temperature is unchanged. If temperature increase, the situation would be more. Okay, so if we are looking at the relative humidity, the trend, diurnal variation of the relative humidity over here. So increase relative humidity occur because it's warmer air. Water vapor molecules are zipping about at such high speed they can unlikely join together and condense. The higher the temperature, the faster the molecule speed. The less likely saturation will occur and the lower relative humidity. As the air temperature lower, the water vapor molecule move more slowly and condensation will occur. Okay. In summary, briefly we can say that with no change in water vapor content, if the situation is with no change of water vapor content, an increase in the air temperature lower the relative humidity, which we call the temperature and relative humidity is inversely related, while a decrease in air temperature raises the relative humidity. So if we look at over the picture in here, the diurnal variation of the relative humidity. So our relative humidity at 6 a.m. is highest because at the 6 a.m. sun rises in the east in the morning. So temperature become, this is red is temperature line and this green is relative humidity line. So at this point our relative humidity is maximum because the temperature is minimum. So as temperature increases during the day, 6, 7, 8, 6, 7, 8, 9, 10, 11, 12. So see, the temperature is increasing, the relative humidity is decreasing. So at the time around 3 p.m. to 5 p.m., the temperature is highest. because due to the incoming solar radiation and also the Earth infrared terrestrial radiation, both together added and resulting in highest temperature over here at time of the 3 p.m. to 5 p.m. At that time, the relative humidity is minimum. So this graph shows our diurnal variation of relative humidity, and it is given that there is no additional water is being added to the atmosphere. So by far we know that relative humidity is water vapor content divided by water vapor capacity, and other word we can say actual vapor pressure divided by saturation vapor pressure, and we multiply that by 100% because relative humidity is a ratio, and the ratio always be in percentage. Okay, so I think we have understanding about details of relative humidity. Thank you.